All right, let's jump right in with a big question. What if we could build a computer that actually works like a human brain? That's not science fiction. It's the core idea behind something called neuromorphic computing. We're talking about a totally revolutionary approach that basically copies the brain's own blueprint to create some seriously efficient AI.
Okay, so think about this for a second. Your brain, the one you're using to listen to me right now, it runs on about the same amount of power as a dim light bulb, a dim one, and yet it can run circles around a supercomputer that needs megawatts of energy, enough to power a small town. So how is that even possible? Well, the answer to that question could literally rewrite the future of AI.
So, to really get why we'd even need to build computers that mimic the brain, we first have to look at a huge problem that's kind of sneaking up on us, what some are calling the AI energy crisis.
Look, the AI we have today, it's doing some absolutely mind-blowing things, no doubt about it. But there's a catch. It's incredibly power-hungry. Just running these massive models in the cloud uses up enormous amounts of electricity. And, that becomes a massive problem when you get to what we call edge devices. Basically, anything that isn't plugged into a wall. We're talking about your phone, a drone, a smart sensor in a factory. All these things need to be smart, but they also have to sip power, not guzzle it.
So, the root of this energy problem, believe it or not, goes way back. We're talking about a computer design from the 1940s. It's called the von Neumann architecture, and it's what pretty much every computer today is still based on. And it has this one fundamental flaw, something called the von Neumann bottleneck. The best way to think about it is like a single one-lane highway connecting the processor, the brain of the chip, and the memory. Data and instructions have to constantly travel back and forth on this one little road, and they get stuck in a massive traffic jam. All that shuttling around just wastes a ton of time and energy.
And this isn't just a hardware problem. The famous computer scientist John Backus, way back in 1977, he called it an intellectual bottleneck. He argued that for, over 70 years now, this design has locked us into this really rigid, one-step-at-a-time way of computing, which, if you think about it, is the complete opposite of how our brains work.
And this image here really lays it all out perfectly. See on the left? That's the traditional setup. You've got the processor and the memory as two separate boxes, creating that traffic jam we were just talking about. But then, look at the right. That's the neuromorphic approach. It weaves the processing and memory together, just like the neurons and synapses in our brain. And by doing that, it gets rid of that bottleneck completely.
Okay, so if the old blueprint is broken, where do we find a better one? Well, it turns out the most incredible computer ever designed has been right inside our heads this whole time. Just look at this comparison for a second, because these numbers are absolutely staggering. Your brain, it sips on about 20 watts of power. A supercomputer, we're talking megawatts, millions of watts. Your brain does everything all at once, it's massively parallel. A normal computer, it's mostly sequential, doing things one by one. And here's the real kicker, your brain is event-driven. Neurons only fire up when something new happens. But a standard computer chip, it's just always on, constantly running, burning power even when it's just sitting there waiting for something to do.
So this brings us to a really simple but powerful question, right? Why are we trying so hard to make these old, inefficient designs a little bit faster when we could just build entirely new computers that actually work like a brain? And that, right there, is the promise of neuromorphic computing. It's not just a small tweak, it's a totally different way of thinking that copies the brain's own, incredibly efficient blueprint. Okay, so here's the most important thing to get. Neuromorphic computing isn't just about making faster chips. Not at all. It's a complete paradigm shift. It's about actually building systems with artificial neurons and synapses that process information in a way that's just fundamentally more efficient, and maybe even more intelligent.
So how does this actually work in practice? Well, it all starts with a special kind of AI model called a spiking neural network. Then you develop custom algorithms to train that network, and you map the whole thing onto a piece of specialized, super low-power neuromorphic hardware. Once that's done, this hardware can do its thing, recognizing an image, understanding a sound, with just incredible efficiency.
It really all boils down to a few key ideas. First, instead of just churning through data constantly, these systems use what are called spiking neural networks. I love this analogy. Think of it like the system is using an efficient Morse code, instead of just shouting all the time. The artificial neurons only send out these little spikes of information when something actually important happens. This is that event-driven thing we mentioned. It means the chip is basically asleep most of the time, which saves a huge amount of power. And of course, by smashing memory and processing together, it finally solves that old von Neumann bottleneck.
And I want to be really clear. This isn't just some wacky idea in a research lab anymore. No way. There is a massive global race happening right now, with billions and billions of dollars pouring in to build these brain-like chips and get them out into the real world.
And when I say massive, I really mean it. The market for this tech is projected to absolutely explode. We're talking over $55 billion within the next decade. You just don't see numbers like that unless people are betting this is going to be a foundational technology for the entire future of AI.
So, who's actually in on this race? Well, basically everyone who's anyone in tech. You've got the giants like Intel and IBM, of course, but you also have this whole explosion of super smart venture-backed startups. And on top of that, you have massive government research programs pouring money into this in the US, in Europe, and in China. This isn't just a cool project, it's become a global strategic priority.
And here is the proof. This is why everyone is so incredibly excited. This chart shows how much energy it takes to do a single AI task. Now, those big blue and orange bars, that's your standard CPUs and GPUs. Now, look at the tiny little green and red bars. Those are neuromorphic chips like Intel's Loihi. They're not just a little smaller, they are tiny. This isn't a small improvement, folks. This is a revolutionary leap in efficiency. So the big takeaway here is just staggering. For the right kind of tasks, these new chips are showing up to a 10-fold improvement, not just in energy efficiency, but in speed too. That is a complete game changer for where and how we can deploy AI. Okay, so what does all this actually mean for you, in your life? Well, it could mean AI running on your phone for days, instead of just hours on a single charge. It means drones and robots that are way smarter and can react instantly to what's going on around them. Imagine wearable health sensors that don't just log your heart rate, but can actually analyze it in real time and warn you if something is wrong. This is all about making AI truly part of our world, genuinely useful in our day-to-day lives.
Okay, but if this tech is so amazing, you're probably wondering, why isn't it in my phone already? And that's a fair question. The truth is, like any brand new frontier, there are still some pretty significant mountains to climb.
Really, the biggest hurdles right now are on the software side of things. You can't just program these chips the old way. It takes a completely new way of thinking, a whole new skill set, and the software tools just aren't there yet. They're nowhere near as developed as mature platforms like TensorFlow that everyone uses for regular AI. And then, of course, there's the ultimate challenge. The human brain has 86 billion neurons. Trying to replicate that sheer scale and complexity, yeah, we're still a long, long way from that.
And that brings us to the final, really big thought here. As we get better and better at mimicking the brain's actual architecture, we have to stop and ask a pretty profound question. Are we just building a better, more efficient computer? Or are we actually taking the very first steps toward creating a fundamentally new kind of intelligence? The answer to that question is probably going to define the next century of technology.